In this video, I want to discuss a wonderful theorem called L'Hopital's theorem. L'Hopital's theorem helps you to calculate certain difficult limits. It's applicable to certain difficult limits of discontinuous functions. All right. Let me remind you that if a function is continuous, the limits are all sunshine. For example, x squared, any polynomial for that matter, is continuous everywhere. The limit of x squared as x approaches 3. All you have to do is evaluate the function at 3 and you're done. Okay? However, don't assume you can do that for every limit. Okay? Try this one, sine x over x as x approaches 0. If you try to evaluate the function at x equal to 0, you will get 0 over 0. Okay, so this is discontinuous at x equal to 0. Now, what L'Hopital's theorem allows us to do for this situation is simply replace the fraction with a new fraction such that the new numerator and denominator are the derivatives of the old numerator and denominator. Okay, the derivative of sine is cosine. The derivative of x is 1. Okay, that's a doable limit now because cosine of x over 1 is continuous. So immediately we can get the answer of 1. All right. Now what I want to do before I continue is prove L'Hopital's rule for a certain general situation, and then I'll do some more examples. Okay. Here is the situation I'm going to prove, and then other cases I'll just mention but not prove. So the limit of x as x approaches some arbitrary number a of f of x over g of x equals question mark f prime of a over g prime of a. That's what we are trying to establish, whether that's true. If the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0. So this is the situation we were up against when we did the limit of sine x over x, right? The top limit was 0, the bottom limit was 0, the fraction gave 0 over 0, so we were out of luck, okay? This wonderful result is going to work. I'm going to prove it for a certain specific class of functions. Okay, I'm going to prove it for adding this specific assumption. F of x, g of x, as well as f prime of x and g prime of x are continuous. Okay, so the limit of the top and bottom is 0. But also the top and bottom functions are continuous, and not only that, but their derivatives are continuous. Okay? Now for that situation, and that, by the way, that comes up a lot. Sine and cosine are continuous as well as their derivatives. Any polynomial is continuous as well as its derivative. Okay, so for this wonderful situation, let's do the following. Let's do some manipulations on the original left side. Do you agree that I can subtract 0 from the top and bottom? I hope you agree. That doesn't change the answer. Do you also agree that I can substitute something else equal to 0, like f of a? Why does f of a equal 0, you ask? Because remember what it means for a function to be continuous. Okay, that means that the limit as x approach, let's say it's continuous at x equal to a. That means that the limit as of as x approaches a is equal to the function value at a. Okay, so the original assumption of the two functions having limits equal to 0, also now because they're continuous, that's equal to f of a, and then the other one g of a. All right, so moving right along, let me also now divide the top and bottom by the same number, x minus c, or the same expression, excuse me. Okay, so, and in closing, the limit of a function is the limit of the top divided by the limit of the bottom. But notice that the limit of the top is f prime of a. Notice that the limit of the bottom is g prime of a for a situation where the functions are differentiable, continuous, and the derivatives themselves are continuous. Okay, so there you have it. Okay, I've proved it for the case for the 0 over 0 situation. It's also true if the limits gave you infinity over infinity, although I'm not going to prove that. All right, so let's now finish with a few more examples. And let me make one comment. People usually, not usually, but sometimes they get so excited by L'Hopital's theorem that they want to, every time they see a fraction, they want to take the derivative of the top and bottom. Okay, this trick only works in a quote-unquote weird situation. In other words, if you have 0 over 0 or infinity over infinity. If you don't have any of those types of weirdness, you can't use L'Hopital's rule. Okay, so it's kind of funny in that it only works in the tricky cases when you need it to work. Okay, all right, so in closing, here's a few more examples. So the limit as x approaches 2 of x cubed minus 7x squared plus 10x divided by x squared plus x minus 6. Now, let me repeat, you have to first check to make sure you have weirdness, okay? If it's continuous at x equal to 2, I would simply evaluate the fraction at x equal to 2 and I'm done, period. No need for L'Hopital's rule, okay? So mentally plug in 2 into the top and bottom. You'll see that this is a 0 over 0 situation, okay? So in that case, we can go ahead and we're allowed to use L'Hopital's rule. So the derivative of the top is 3x squared minus 14x plus 10. The derivative of the bottom is 2x plus 1. Okay, now we do not have a 0 over 0 situation. It's continuous at x equal to 2. Hallelujah. So we just plug in 2. So 3 times 2 squared minus 14 times 2 plus 10. On the bottom, 2 times 2 plus 1. So 3 times 4 minus 28 plus 10 divided by 5. 12, 22 minus 28 is minus 6. And then there you go. All right? And then lastly, let's do one more example. The limit of x approaches 4 of x minus 4 over square root of x minus 2. Once again, do a quick check to make sure you got weirdness. So plugging in 4, yes, you have a 0 over 0 situation. Taking the derivative of the top, 1. Taking the derivative of the bottom, you can write it, you can use the power rule, or you can write it in this equivalent way. You'll see that the power rule gives you that expression for the derivative of the bottom. Okay, now it's continuous, so we can plug in 4. So we get the inverse of 1 over 4, which is 4. All right, there you go.